One whole port, if you are sending for communication, you have 8 bits, and each particular pin, each time you will be sending something like E, then D, E, D, D, E, D. That means in 7 machine cycles you are finishing the operation.
Okay.
Okay, I have something like 8, one whole port. If I am assigning, I will have to be like, here I will be sending 0, 1, 1, 0, 0, 1, 0, 1. That means at a time I am sending 8 bits. So when you are going for serial communication, if you want to send 7 characters, it will take 56 machine cycles. But when you go for parallel communication, for 8 characters, it will take 8 machine cycles.
Yeah, okay.
Okay, that means here the thing is speed. 56 machine cycles is taking more time when compared to 8 machine cycles, 7 machine cycles.
Yeah. Yes.
Right. So speed is a matter, but along with speed comes cost.
Okay.
The cost will increase. So for small or big device, it depends on my requirement, that whether I am going to go for that much cost or not. So cost is one factor we will have to think. Speed is another factor. Other than this, there is one problem where serial communication is fine. Like if I have some defect, somewhere I am getting one defect. So when you go for serial communication, either I'll get corrected data or corrupted data. That's it. If I'm getting corrupted data, I will be like, yes, something is wrong with my cable. Fine.
Okay.
But when you go for parallel communication, as you have 8 wires or 8 wires, it is very difficult to locate where is the error or in which wire the problem is.
Okay.
Okay, so there it is somewhat like, it's not that you cannot, but yes, that is also one factor. So then what is good, whether you should go for parallel communication or serial communication, it completely depends on our requirement. Okay, basically when you are doing small distance communication, you'll go for parallel communication, because the cost will be as the length of the wire will be less, and it is very easy to detect errors in small length. Then you will be going for parallel communication, like you say printer.
Okay.
But when you have long distance communication, you will be going for serial communication.
Okay.
You will be sending 1 bit by 1 bit. Now here, how this serial communication works, if you say how this is working is, in this, here you will have half duplex and full duplex communication. In half duplex you will have simplex communication. Now in simplex communication, you will have one transmitter and one receiver. Okay, transmitter we are calling it as CX, and receiver we are calling it as RX. So one is one transmitter and the other is receiver. Here only transmitter will be able to transmit data, and receiver will not be able to respond back. This is your simplex communication. Okay, I'll tell you an example of where you are using the simplex communication. Radios. Okay, they are able to transmit the data, and you are able to hear all whatever they are saying, but you are not able to send any information to radio.
Yeah.
So there this simplex communication works. You will be able to send data, but you will not be able to receive it. Then you have half duplex communication. In half duplex communication, you will have transmitter as well as receiver. Okay, and you will have only one. You will be able to transmit data from receiver to transmitter and transmitter to receiver, but you will have only one line. That means either I will be able to transmit data or I will be able to receive data. I can transmit as well as receive, no doubt.
Okay.
I'll be able to transmit from transmitter to receiver and from transmitter from receiver to transmitter.
Receiver
But
to
as I
transmitter.
have only one line, only one person can use it.
Okay.
Okay. Uh, like you have something like this walkie-talkies.
Okay.
Okay. If at all, if I am transmitting, all the other three, all the other will be able to receive the signals. But we can only use one at a time.
Okay.
Okay. Now the last one is you will have transmit. This is full duplex. This is half duplex, and this is full duplex. In full duplex communication, you will have transmitter as well as receiver. Number of transmitters and receiver. And the good thing will be like here you will have separate lines for transmitter as well as for receiver. That means two wires will be there, one for transmitting and the other for receiving. In half duplex communication, simultaneous operations are not available. That means if I am transmitting at a time, the other person can't transmit.
Okay.
Only the other can receive. Here we have two wires for it, one for transmitter and the other for receiver. So
Okay.
whenever you simultaneously a transmitter can transmit and the other one can receive and the other outsider can transmit and our microcontroller can receive. That means this TX and RX is there in our microcontroller. Okay, so we do have two separate lines. If you remember, in our port, three pins are there, P3.4 and P3.5, which are there as TX and RX.
Yeah. Yes.
Okay, so that TX and RX you have for this microcontroller, and this RX and TX are for external device.
Okay.
So at a time simultaneously you can send as well as you can receive your data.
Okay.
Okay, so we will be again you have something like in this also you again one more parameter is there, whether it is an asynchronous mode of communication or synchronous mode of communication.
Okay.
Now here what is this asynchronous and synchronous, we will see both, but as of now we will be using here UART. UART is universal asynchronous receiver transmitter. Here we will be using UART, universal asynchronous. In USART you have universal synchronous asynchronous receiver transmitter. But here we don't have synchronous mode of communication, we'll be using only asynchronous mode of communication. Now synchronous mode of communication is whenever you are doing it with respect to time.
Okay.
I'll be concentrating on synchronous mode of communication when we are doing something like SPI or I2C communication. They both are synchronous mode of communication. So we will see there what is this synchronous mode. It is with respect to time, SPI and I2C. But here we will be using only asynchronous mode of communication. So asynchronous mode of communication will be done with your this is like character oriented transmission will be there. We'll be sending it with respect to your data characters.
Okay.
Okay. There are actually two things. One is character oriented and the other is block oriented data transfers. Here we will be using character oriented transmissions, which I will say you. Okay. Now what is this character oriented? In this character oriented, what happens is you will have, now as I said, I want to transmit some data. Okay. Which is like I want to transmit A, B and C. Okay, I have to transmit this A, B and C. So in this character oriented transmissions, what happen is you will be placing your data here. As I said you, A is nothing but 65.
Yeah.
I gave you one program program, right, that convert your characters into ASCII characters and print. So there for each and every character you will have a number. So here for capital A you will have 65. Capital A is
Okay.
65 and capital Z is 90. 26 characters.
Okay.
Okay. Capital Z is 90. Okay. And then small a is from 90 to 122. Small a is 90. Here small a is 90 and capital small Z is 122. Some value is there. Okay. Small Z is 122. 122. 26. Add 26 to it. You'll get it. Okay. So here when you say A, here in character oriented data, what you will have is, first you will have to transmit this 65. Now this 65 is placed in between start and stop bit. This you call it as your character oriented transmission, because you are placing only one character at a time.
Okay.
Okay. Now when in your block oriented transmission, what happens is you will be placing this whole ABC at a time.
Okay.
Okay. So here I am using, even though I have to send this ABC three characters, I will be taking 3 mission cycles and I will be placing each and every character in between start as well as stop. Okay, so here what is this start and stop, and how it will know that this, and what is this called is, this placing this data in start and stop bit, you call it as data framing. You are framing your data. Okay, so this is called data framing. Now what happens here is, first you will have something like start bit, stop bit. Now in this, first you will have to send a start bit and then you will be sending your data and then send a stop bit. You can have one stop bit or two stop bit, that you can select it. But how, now the question is how it will know what is the stop bit and start bit. Okay, so always here you will have something like depending, you will have to see the data sheet. Now first this is my start bit. When you have a data from low to high, when you are sending a signal from high to low, sorry, when you are sending a signal from high to low, here you are saying that this is my start bit. Okay, and once you receive this signal of high to low, it will understand that now whatever is going to come next is my data.
Okay.
So it will receive something like 8 bits of data, and after 8 bits again you will have a bit from low to high or high to low, depending on what you are selecting. So here if you have from high to low and then from again one high to low and again from one high to low, then you call it as start. This bit is your start and this bit is your stop.
Okay.
Okay, so it will understand that. Now when you send something like how, now your question might be how it will know that this is my stop bit and this is my start bit. I can assume that okay, from here only I am starting my data. This is also high to low signal.
Okay.
This is also 1 and this is 0. So when if you are sending something like 1 to 0, how it will understand that, oh, my data is starting here. That data framing is already set by your register. Okay, that we will see in register. But basically whenever you are sending a signal from high to low, 8 bits of whenever you say a high to low signal, it will understand, okay, this is my start of data, next 8 bits is my data. It might be your start or stop. If you are doing some mistake and you are sending a signal, then also it will consider it as data only, and after 8 bits of data, then only whatever next signal is, it will consider it as stop signal.
Okay.
Basically, in character-oriented data, you will have a start bit, 8 bits of data, and stop bit.
Okay.
Okay, so this is asynchronous. This is full duplex communication. This is UART, which is universal synchronous universal synchronous reverse communication, using full duplex communication and using a data framing of start and stop bit. Okay,
Oh,
now one note here. You use any serial communication wherever you are using UART. It might be 8051 or it might be anywhere in embedded systems. If you are using UART, the main concept behind this will be same. That means if you are working with BeagleBone, that you are working with Raspberry Pi or STM32 or AVR, anywhere, the concept will be for timers, for counters, for UART, for SPI, I2C will be same. The only thing that will change is how it is sending start and stop bit, how we need to select it, and how many wires or which mode it is using. Okay,
okay.
but basic operation of your UART peripheral will be same. Once you
Okay.
get this, it will be same anywhere. The only thing is the pins will change, the naming concepts, the registers will change. But
No.
basic will be remaining same. Okay. Now here, okay. Now the next question is, I am sending. It is clear up to here.
Yeah.
Now the next question is like, fine. I am sending some data, and you are receiving some data.
Okay.
I am sending 7 bits of data. That means it is taking some 56 machine cycles. The thing is, I am sending some data at my speed, but whether
Okay.
you are receiving your data at my speed or not, how will I know? Right? My
Okay.
speed of
Yeah.
communication and your speed of communication might be different. So whatever I am sending, you might not be receiving it, or whatever you are sending, I might not be receiving it properly. So if this happens, then our data will be corrupted.
Okay.
So for that reason, we will have something like, we should have same speed. So here that
Okay.
speed we call it as baud rate. Here we call it as baud rate. So basically baud rate is nothing but speed, or speed of data transfer, or
Okay.
you can data transfer
Okay.
rate, anything. So whatever device you connect, if I'm using a speed of suppose 9600, so now if I'm using data speed of 9600 Hertz, you are supposed to receive it at that particular 9600 bits per second. Then you will also be receiving that at 9600 bits per second. If you are receiving it at same baud rate, then our data will not be corrupted.
Okay.
Basically, you will have some speed already defined, like you have 9600
Yeah.
bits per second, BPS. Then you have something like next speed will be 18,000. Already these are defined. Okay, 8 and 9600, 18,000. Then you have something like 36,000, or you would have heard something like 115200, 1 Mbps, 2 Mbps. All these speeds are already defined. So you will have to select one of them.
Okay.
Okay, you need not select your transfer data rates already. Why? Because the thing is, now you can say that it's my wish that I want to send my data. I want to send my data at suppose 8,000 bits per second. No problem. You can send the data, but that speed has to be available with the device you are sending it.
Okay.
Okay, so that's why this standard speeds are already there. If you see this, you will be able to see in your laptops also, or you can say that in your Wi-Fi. they will be asking you will have 50 Mbps or 100 okay, 1 Mbps, 2 Mbps, 50 Mbps speed, Wi-Fi speed, broadband.
Yeah.
Okay, so already those predefined data rates are already there. We need to select one of them.
No.
Okay, now the next problem come here is how to connect that with system if I want to communicate, or if I want to connect suppose you have this any devices if I want to connect to, like I have GPS or GSM module. Okay,
Okay.
GPS suppose I want to connect it with GPS. Now my problem is how to connect with that GPS. I have only port pins. Two
Okay.
pins I have. One is CX and the other is RX. Now I want to communicate that with my GPS device. Now what to do? So here the problem will be like whatever data or whatever logics they have set. Or suppose you have system. So there here you will there they will have something like basically everyone understand only one signal, that is if it is high suppose you are saying 5 volts, if it is 5 volts it is high logic, and if it is 0 volts it is low logic.
No. Okay.
Okay, so here we
Yeah.
need to follow the theme. So
Okay.
when this started there was something like different logic levels.
Okay.
But now the logic levels have changed. Now we are working only with something like -3 to -25 -25 volts and +3 to +25 volts. Previously they used to
Okay.
have only two, 0 and 5 volts. But now we are working anywhere in between -3 to -25 or +3 to +25 volts. So here to make it compatible with our devices, we have one standard called RS232. RS232 standard. This is not a device. This is simply a
Okay.
standard which says that if you have something like RS232, it says that if at all, if any voltage is there in between -3 to -25, you call it as 0, logic 0. You consider it as logic 0. And if
Okay.
you have any voltage which is in between +3 to +25, you call it as logic 1. Okay.
Okay.
Now I have again one more problem there. Our microcontroller doesn't understand all these things. Our microcontroller, as I said, it understands only two logic, either 0 volts or 5 volts. That's it.
Yeah.
But here we have something like -3 to -25, +3 to +25. Anything, any voltage I can have. Now to make these compatible, these two things compatible, we need one converter here. Okay, is it clear? Suppose you are working with your laptop. Okay, I
Okay.
want to connect my microcontroller with laptop. My
Okay.
laptop will have different. My laptop will have different voltages. I mean not different voltages, but your laptop is neither working at 5 volts. It's not working at 5 volts, right?
Yeah. 20 all.
I want to send some signals, and that signals. Just a second, Kaushik.
Okay.
Hello? Hello?
Yeah. Yeah.
So here, whenever we want to connect, there might be some signals which might not be only 1 and 0 or 5 volts in your laptop. Okay, so it might be working on this particular logic. Okay,
Okay.
so here what we have to do is we have to make this compatible. This particular thing is called RS232 standards to convert this. So for that we are using one converter called MAX232. This is a physical device. MAX232 is physical device. RS232 is standard. It
Okay.
is standard which says this.
Okay.
Okay. So to implement this, we are using MAX232. So in MAX232, what happens is whenever you are connecting any device which is using this particular logic, TTL compatible. So here what it will do is whenever you get a signal from -3 to -25, it will convert. It will make your laptop not laptop, your microcontroller understand that it is logic 0.
Okay.
Whenever there is any signal in between +3 to +25, it will say that it is logic 1. So it no more needs this 0 or 5 volts logic when you are using this MAX232 device. Okay, so here you have some particular you have seen desktop. I mean, sorry, not desktop, you would have seen definitely, but did you observe something like you will have blue color cables with ending with two blue color I'll show you just a second.
Okay.
There you will have 25 pins on it. So basically what happens is whenever you are using this, you might be connecting different company devices, right? So just to say that everything what, one second, are you able to see this you would have seen,
Yeah. CAN
right?
adapters, like. Yeah.
Sorry,
CAN adapters, right?
I didn't, I mean it's not
CAN.
audible.
CAN key. Okay. Hello.
Okay, so this is particular thing which you are using. So this is a standard which all the manufacturers are using, such that there should be no problem with any company devices which they are communicating. This is done by Electronic Industries Association.
Okay.
Okay, so now when you are using this particular standard, here you will have some particular pins. If you see this, one second. You're able to see this pin diagram.
Yeah.
Now, when you see this, here you have some pin called received data and transmit data, pin 2 and pin 3. Here you will have two type of connectors. One is DB25 connectors and one is DB9 connectors. Previously, that means here you will have this pins, number of pins you have. So basically previously 25 pin connectors used to come, but nowadays no 25 pin connectors are available. Almost everyone uses only 9-bit connectors, 9 pin connectors. This you call it as DB9. RS232 pin out. So here everywhere this particular pins RS232 will use this particular things only. Basic what we are interested in, this pin 2 and pin 3. This is RxD and this is CxD, and the other pin is ground. Okay, the rest of it depends on what you are sending. Suppose one thing is data terminal ready, DTR. DTR is to give a signal that it is ready for ready with data. Okay. Your terminal is either ready to send it the data or receive the data.
Okay.
you have data carrier detect pin 1. It says that okay, it has detected some data. Similarly, you have data set ready for sending, request to send. It will ask you whether if at all if your data is ready, then it will request your permission to send the data, clear to send.
Okay.
Similarly, you have all these pins which you will be which you will have in this RS232 standard pinout diagram. Okay, but
Okay.
generally whenever we are using right now, we are using RxD and TxD, and nowadays these DB9 pins are not used. Simply if we use RxD, TxD and ground, that will be sufficient for devices. You
Okay.
can see these pins in old signals only, old devices only.
Okay.
Okay, so here next, as I said you, we cannot communicate with this without one connector called MAX232 converter.
Okay.
Okay, so what does this MAX converter do is, one second, I'll have to select this screen. Yeah, so what this will do is, you will have something like now you will have TXD and RXD of your microcontroller, and then here you will have your microcontroller TXD and RXD pin,
Okay.
and here you have receiver, and then these two pins are not directly connected to your GPS module,
Okay.
RxD and TXD. Here TXD is connected to RxD and RxD is connected to TXD, but before this communication happens, you will have one converter, and that converter is MAX232 physical device, as I said.
No.
Okay, so here one side is your TTL side and the other is your RS232 side.
Okay.
Basically, what it does contain is simply a uh, what a gate. Okay, so here if you have any high signal or low signal, it is simply converting it into it. So here, oh sorry, this is not TXT, this is also T and this is R. Your output of your, oh not this is, sorry, I got confused. This is receiver and this is transmitter only, but here you will have input as one value and output as another value. Okay, so whenever you are sending any signal, it will simply convert it and it will send you the output. It will have a NOT gate inside it.
Okay.
Hello?
Yeah. Hello.
Hello, is it
Can you hear
audible?
me?
Yeah,
Yeah,
yeah.
for me it's audible.
Ah, okay. So before sending any signal directly, so whatever your voltage levels here are, suppose it is 5 volts or any 0 volts, it's sending the same signal without changing it, but which is compatible with this TXD.
Okay.
Okay. Oh, sorry, RXD. This is TXD. So basically here you are using it for, this is your input and this is your output. This is your input again, this is your main input and this is your main output, but here again you will be sending one signal and you will be receiving another signal, which is here you call it as TTL logic, which is your 0 to 5 volts logic, and here you call it as RS232 logic, which is from -3 to -25 and +3 to
Plus 3 to
+25.
plus 20. Okay.
Okay, it is
Yeah.
not going to change your signal, it will simply transmit the same thing.
Okay.
Okay, so you will be using this inside your, this is external device. So basically your 8051 doesn't come with this MAX232. If you are using it, you will have to buy another, buy one MAX232 converter. Okay,
Okay.
so coming to your next things, okay, this is Fine. Now, as I said, coming to your baud rate. Now here comes your logic of using your 11.0592 megahertz crystal oscillator. Okay. So what happens here is, as I said, you have some particular predefined baud rates already available, which are something like I said 9600, 4800, just divide it by 2. And if you want to go up, you will have to multiply it with 2. 9600 into 2.
Okay.
Okay. Then 2400. These are predefined one, and the other one is 1200. These particular 4 baud rates are available for 8051 communication.
Okay.
Okay. Upside you have till 2 Mbps. Just to multiply 9600 into 2. Whatever you get, again value into 2. You will be getting somewhere around still 1 Mbps you will get. But here for 8051 only these 4 baud rates are available.
Okay.
Okay. Now how we are getting this baud rate? That means I have to send 9600 bits per second. Okay. So
Okay.
what to do and how to receive this? So basically what we are doing, first of all, we are using one frequency, particular frequency called 11.0592 megahertz crystal oscillator, right?
Yeah.
592 into 10 power 6 megahertz. This we are dividing with 12 by, because we have machine cycles, right?
Yeah.
12 pulses constitute one machine cycle.
Okay.
So we will get something like 921.6 kilohertz.
Okay.
Okay. Why we are using 12 is because simply each operation requires one machine cycle, and one machine cycle constitutes of 12
12.
pulses. Okay. So 921.6 kilohertz we will get now. Okay. Now here
No.
what happens is, this is something like 921. Now for this you will have to divide it by 32.
Okay.
Okay. Then you will get a value called 28,800.
Okay.
Okay. Why I will say you. But you will have to divide it by 32. Then you will get 28,800. Okay. 28,800. Now when you get this 28,800, what happens is, this we will have 28,800, we will get this baud rate actually. Okay. Now you see, if you divide this 28,800 by 3, what you
Okay.
will get is 9,600.
Yeah.
Okay. And if you divide it by something like 12, 28,800, if you divide it by 12, you will get 2,400.
Okay.
Second one, sorry, what it is, 2,400, which is your third one. Similarly, if you divide it by 6,
6.
you will get 4,800, and if you divide it
4,800.
by 24, you will get 1,200.
Yeah.
Okay. So this particular 32 value is defined by your microcontroller itself. It is
Okay.
done by your machinery circuitry only. That this has to be particularly for UART, you will have to divide it by 32.
Yeah.
This is fine.
Yeah.
You will get 12 machine
Yeah.
cycles, you will get 921.6 kilohertz. You have to divide it by 32, which is predefined. It is predefined in circuitry. You will get, basically you are getting 28,800, and upon dividing this 28,800 by 3, 6, 12 or 24, you are getting your desired baud rate. Okay. Now This
Okay.
32 what I said is already defined in your circuitry in microcontroller itself. But this
Okay.
3, 6, 12 and 24 we will have to select.
Okay.
So how we will select that is using timer 1.
Okay.
Okay, already we have seen that when you are using your timer, then if you are making it work like something like counter, what happens? 0 to 6553. Once your timer what increases, if you load a value 0 to 65513, 65535, it will be counting it like 1, right?
Yeah.
When you are using a counting operation here, what happens is when you are using 28,800 only. Okay, hello,
Okay. Yeah.
is it audible? Now
Yeah.
what
Yeah.
happens
Yes.
here is you will be using your timer. Your timer will be continuously running a particular value. Okay,
Okay.
so what happens, for example here it will use something like these particular 3 pulses, it will consider it as 1. These 3 next to 3 it will consider it as 2. So you will be generating 28,800 hertz.
Okay.
28,800 hertz only. But what it will do is this, for 28,800 it will divide it into 3333, 3 pulses as 1. It will count
Okay.
this 28,800 pulses in 3 3 blocks. So 3 pulses constitute 1. Like this, when you divide this 28,800 with 3 pulses, you get basically 9,600. That means each operation will use 3 pulses. Similarly,
Okay.
when you go for 2,400 hertz, 12 pulses constitute your uh, what it will consider it as 1. I don't think you understood here. Now 11.50592 is your basic frequency, right? You're dividing it
Yeah.
by 12. Okay, this 12 how you are getting is simply you are using machine cycles. So these, if you say all these are 12 machine cycles, you will consider it as
Okay.
one machine cycle, right? Now
Yeah.
don't think of these machine cycles. Don't think of this machine
Okay.
cycle, simply consider it as pulses.
Okay.
Okay, when I am dividing it by 12, you will get 921.6. So how you are saying it as 921.6? This 11, if you are dividing it, suppose these are all 12. Okay, so basically
Okay.
these 12 you are calling it as 1. 12 as 1. Then next set of 12 as 2. Then third set of 12 as 3.
Okay.
12 pulses is equal to 1. 12 pulses is equal to 1 if I say, then 921.6 kilohertz you will then you will get this 921.6 as when you consider it as like 12 is equal to how I can say you 12 is equal to 1.
Divided by 12?
No, I'm not saying about divided. You can understand the logic. What I'm trying to say here is, see how you will know. This is not about calculation part I'm saying.
Okay.
I'm not saying calculation part. How it is considering it as speed I'm saying.
Okay.
Basically, if you say, okay, if you consider your time, okay, we have some
Okay.
smallest unit of time as 60 seconds, right? And 60 seconds
Yes.
constitute 1 minute.
Yes.
60 seconds constitute 1 minute, and again 60 minutes constitute 1 hour, right?
Yeah.
Right, but the basic unit is nothing but your seconds only.
Yeah.
You are considering this seconds, you are constituting these seconds, and you are making one group which you call it as like 60, a group of 60 seconds, you are calling it as 1 minute.
Okay.
Right, similarly here also these 12 pulses, that means what you are basically doing is, if you have something like 100, if you want to divide this 100 in 10, you are continuing like 1 to 10 is one cycle only,
Yes.
right? 11 to 20 you are considering it as second cycle.
Yeah.
That operation till 28,800 is done by your circuitry itself.
Okay.
Okay, so you are using this 11.0592 megahertz only, but you are simply dividing it. Dividing in the sense, even though you have 11.0592, you will not consider it like these many pulses. I am saying that 28,800. I am 100 is equal to 1 only. I am saying. In that way
Okay.
you get 9,600. So basically when you have 28,800, 88,800 you are dividing it into 3 parts. That means 1 to 3 is 1 only. 4 to 6 is another 2.
Okay.
7 to 9 is 3. 10 to
Okay.
12 is 4.
Okay.
You understood? No, I don't think
Mm.
so.
That's
Okay, I'll try one more time.
okay.
Don't think of all these frequencies or everything. Here just
Okay.
I'll say you simple logic like how we are dividing the frequency. I am saying you. Now here
Okay.
this is like 1, right?
Yeah.
This is 2. Oh, 1 cycle. This is 2 cycle. This is your third cycle, or you consider this as 1. This is your 2. I'll write it here.
Okay.
1, 2, 3. This is your 4, 5, 6, 7, 8, 9 and 10. Okay, I am using 12. Now if you count this, you have 12. Okay,
Yeah.
this is simply 12. Now but I don't want to, I want to even divide it. Now what I'll do is I'll say that these I will consider it as 1 only.
Okay.
This is my 4. Here I am dividing it by 2. That means you can use in place of 2 pulses, you are using 2 pulses but calling it as 1 only.
Okay.
So you have divided this particular 12 pulses into 6. So even though you have 12 pulses, you are constituting 2 pulses to form 1.
Okay.
Similarly, what I'll do again is I'll consider this as 1 only. Now
Okay.
this is my 2 and this is my 3.
Okay.
Okay, so now I have only 3 even though I have 12. So basically what I am doing, I am counting even though I have this 4 till 4 I am considering it as 1 only. 1
Okay.
pulse. 5 to 8 I am
Yeah.
considering second pulse. 9 to 12 I am considering it as third pulse.
Okay.
In this way you are dividing your frequency.
Okay.
11.0592 you are dividing it by 12, you are getting 921.6.
Okay.
Okay,
Yeah.
this whole 12 pulses you are considering it as 1. You get 921.6 kilohertz. 921.6 you are dividing it by 32. You are getting
Yeah.
28,800. Now this 28,800 I have. If I divide it by 3, that means if I read it 3 as 1, then I get 9,600. If I read 12 as 1, I get 2,400.
Okay. Depending on what we take, baud rate will change.
Exactly.
That's it.
We will have to
Oh.
select that. Whether you want to go for 9,000, 1,200, 2,400, 4,800 or 9,600.
Okay.
Okay. That we will be selecting it through timer 1.
Okay.
This is already predefined. You cannot use anything else. You have to use timer 1. for this.
Okay.
Timer 1, mode 1.
Okay.
Okay.
Yeah.
Okay. Now
Yeah.
here you will be using, sorry, timer 1, mode 2, not mode 1. Timer 1.
Okay.
And that is predefined. That means one baud rate we are using for timer 1. How we will use it, I'll say you. This is clear?
Yeah.
Okay.
Okay.
So now next thing, you're clear about this, right?
Yes. Yes.
Because basically only this is that matters actually, because rest of it only registers are there. That registers we can understand in
No.
any way. Now you have one register here called buffer register, that you call it as sbuff register. Okay, this is simply a register which is of 8 bits, and here you will be loading data which you want to transmit. Okay, and you will be receiving data here only. This is an 8-bit register.
Okay.
Your register will be loaded. It will be transmitting 1 bit by 1 bit. When you transmit it 1 bit by 1 bit, your sbuff register becomes empty. Okay, that means your data has been transmitted. Okay, fine.
Yeah.
And when you are receiving data, you will be receiving here 1 bit by 1 bit. So
Okay.
when your sbuff becomes full, it means that you have received that particular data. While transmitting, it will be done when your sbuff register becomes empty.
Empty.
And when you receive, when your register becomes full, it means that you have received data.
Okay.
You say 65, here you will have something like 0, 1, 1, 0, 0, 1, 0, 1. So when you transmit this particular bits of data, you are transmitting A. And if you are receiving, then also you will be receiving it 1 by 1.
Okay.
This is first
Yeah.
register which you have in serial communication.
Okay.
Now next register we have is like TCON, we have a register called SCON, which is serial control register.
Okay.
Again, this register is also of 8 bits.
Okay.
Now what do we have in this particular register is, sorry, I'll say you're able to see notepad, right? No, not notepad, whiteboard, right?
Yeah. Yes.
Oh. Here like we have 3 bits for mode selection. SM0, SM1 and SM2. Serial mode 0, serial mode 1, serial mode 2. Okay. And next is called REN. I'll explain each and every bit. And next is your TB8. RB8. TI and RI. This is your SCON register. Now, so as I said here, SM0 and SM1 are for mode selection. SM2 is used when you are using Okay, so as basically right now we are not using any multi-processor communication, we can make this bit as 0. Okay. Next, here this REN is receive enable. When you make this particular bit as 1, then only you will be able to receive data. Okay. And if you say that I want to receive data and you make this particular bit as 0, then you will not be able to receive any data. This is like a lock, you can say. When you open it, then only you will be able to receive data. Okay. And RB8 and TB8, I'll say you what that is. Now, from that time what we are saying is 1 start bit, 8 bits of data and 1 stop bit or 2 stop bits, right?
Yeah.
Have different, as I said, you have some different modes of communication, SM0 and SM1. That means here you have 4 options again, 4 combinations available, 0, 0, 0, 1, 1, 0 and 1, 1. How this differs is, in this particular mode, here we will be using 0, 1. Now in this particular mode, what happens is, you will have 8 bits of data, okay, 1 start bit and 1 stop bit. Okay. In other modes, you will have something like, you will have 8 bits of data, 1 start bit, 2 stop bits. Or you will have something like 9 bits of data, 1 start bit, 1 stop bit. 9 bits of data, 1 start bit, 2 stop bits. In other modes, I am giving. Similarly, you can have 8 bits of data, 1 start bit, 2 stop bits. 9 bits of data, 1 start bit, 1 stop bit. 9 bits of data, 1 start bit, 2 stop bits. We are using only this particular option here. 8 bits of data, 1 start bit, 1 stop bit, 1 stop bit, sorry, not this one, this one. 1 stop bit. Okay. That means each time we are transmitting, we are doing transmission, you have 10 bits of data. 1 start bit, 8 bits of data, 1 stop bit, 10 bits completely. Okay. Suppose I am using 9 bits of data. As I said, we are going to transmit and receive your data in SBUF register.
Yeah.
SBUF register is of 8 bits. If I say I want to have 9 bits of data, then where that 9th bit will go? That 9th bit, if you are using, here it will be. If you are transmitting bit 8. Okay. Okay. So basically you are using here only one particular mode of operation, which is serial mode 1. 8 bits of data, 1 stop bit and 1 start bit. But you do have multiple options available, and this TB8 and RB8 is used only when you go for 9 bits of data. And generally we don't go for 9 bits of data, we go for 8 bits of data only. But there might be some requirement where you need to have 9 bits of data. At that time you will go with this, otherwise this bit value will be 0 only. Okay. So now if you are using constant like 0 1, I am not using multiprocessor communication, then it is 0, right? If I am using transmit operation, this bit will be 0, TB8 will be 0, RB8 will be 0. As I am not using 9 bits of data, then this TI and RI will be 0 only. What is this TI and RI? TI and RI is transmit interrupt flag and receive interrupt flag. Transmit interrupt flag is whenever your transmission is completed, whenever your 10 bits of data is completed, then this bit will become 1, stating that your transmission is complete and you are ready to transmit next byte of data. Okay, and when your SBUF register is full, it will become 1, saying that you have received 1 byte of data. Take it from SBUF register. So these two bits are just indicating. Indication. So this particular value is for transmission. When you say receiving, you will have to say again here same thing, mode is same, SM2 bit will be 0, but receiving is 1 here. Receive enable is 1 and rest of the bits will be 0. Okay. So S mode value will be something like 0x40 and 0x50. Okay. This register is clear? Right. Now, how to do the serial communication programming? So first what we will do is, we will load one particular value in TMOD register. What is that value? As I said we will be using timer 1, mode 2. Auto reload mode we will be using to select baud rate. Okay. If I want to go for, what value I want to go for is, what I'll say, I want timer 9600 suppose. If I want to go with baud rate of 9600, then I will have, right? In my which register is timer 1 register mode 2. Okay, then what we need to do is select the operation, what you want to do, whether you want to receive or transmit. Generally what we do is, we will be always writing this value as 0x50 only, because you are not going to do only transmission operation, you are also receiving, you are also going to do receiving operation. So basically we just enable your receiving option also. So we will be loading your SCON is equal to 0x50. Okay. Now first of all speed selected, and your which is an indication that your transmission has been finished and your SBUF register is empty.
Okay.
Okay. Is it clear?
Yes.
Okay. So we will write one program then. Okay. And one more register we have called PCON register, which I'll say you later. But there in PCON register you have only 1 bit, which is like S mod. Okay, what that particular bit will do is only one bit is there. This is to double the baud rate. That means if you are selecting 1200 and you will make that particular SMOD bit in PCON register as 1, you will get double speed.
Okay.
Which you have in for your 8051. You can
Okay.
double that speed by using this SMOD register. You will
Okay.
get double the speed.
Yes.
Okay, we will see that later, but as of now you just now how to load this value of -3, or sorry, not -3, 3. How to load this as I said, you have to divide this by 3, right? You have to divide 28,000 by 3, right?
Okay. Yeah.
So in tmod register, how we will load that? Either you load -3. Okay, what is -3? It is equivalent to FD.
Okay.
Right? Again,
Yeah.
when your timer again you count 3, it should become 2. Again you count 3, it should become 3. Like that we are dividing. So if you write something like when it is 255, if you take complement of 255, you will get -1.
Okay.
2's complement of -25 is -1. Similarly, here you will get not 2's complement, 1's complement. 1's complement of 255 is -1. 254 is -2. 253 is -3. That means once you go from back side, you will get -1, -2, -3. Okay, 1's complement. Maximum value of 8 bit is 255, right? We are using timer
Yeah.
1 mode 2. In mode 2 you have only TH1 register to be used because it is an 8 bit register, 8 bit mode.
Okay.
2 is an 8 bit mode. 8 bit mode maximum value is 255. I want to count only 3. If you want to count only 3, you will have to load a value 253, 253, 254, 250, right? Which is nothing but FD, FE, FF.
No.
When you count this, your timer flag will become 1. That means one cycle is executed.
Okay.
Okay, so either you can load -3, which is equal to FD. FD is nothing but 3. When you write 255, 255 is FF, right? 255 is FF. When you take 1's complement of 255, it is equivalent to -1. 1's complement.
Okay.
3, 4, 5, 6, 7, 8, 9, no, not 8, 8 bits only. No. So you will be going with something like complement. When you take here 8 bit 2's complement or 1's complement, you take, you will get something like -1, -2, -3. 255 is equivalent to -1.
Okay.
Okay, so in this way you will be using your uh, value which you have to load in timer.
Okay.
Okay, so here we will use this FD, which is nothing but value to get the speed as 9600. Okay,
Okay.
if you use this 9600 and you make SMOD bit in PCON register as 1, SMOD bit in PCON register. Just now I said you have one more register called PCON register, which is power control register. In that first 8th bit is this SMOD bit, only one bit. If you make this bit as 1, 9600, it doubles the speed of 9600. If you have selected
Okay.
9600, the speed will become 19,000. I hope it is clear.
Yeah.
Shall we write a program if it is clear?
Okay.
Now you should have one doubt. The doubt is, now suppose you are using 12 kilohertz or 12 we are using 11.0592 megahertz crystal oscillator. In place of 11.0592, if I will use 12 megahertz, what I'll get is 12 by 12. I'll get 1 kilohertz, right?
Yeah.
I'll not get 921. If I don't get 921, I'll not get this 1 kilohertz. You will be again divided by 32 for serial communication. We are doing this operation only, na?
Yeah.
Right?
Yeah.
But the same thing, if I use 12 megahertz or 11 megahertz crystal oscillator, 11 by 12 or 12 by 12, 1 kilohertz. 1 kilohertz divided by 32, you will not get 28,800. If you don't get 28,800, you will not get this 3. If you will have to find out particular values to get 9,600 or 1200.
Yeah.
Okay, so as we cannot get this particular value 1 by 32, I don't know how much exactly it will be, but it is not 28,800 obviously, but that value when you divide it, if you whatever value you get, if you divide it by 32, I'll just say you what is that value. I don't remember. 1 kilohertz is nothing but 1000 divided by 32, you will get 31.25.
Okay.
Okay, this is 31.25. If you say 31.25, how am I supposed to get this 9,600? Correct?
Yeah.
I'll not be getting 9,600. That's the reason you will go for proper 11.0592. So this crystal oscillator plays an important role for serial communication, and that's why you'll go for this particular value.
Okay.
Okay, 1 kilohertz divided by 32, you're getting somewhere around 31.2.
Yeah.
Okay, and when you do 11.0592, sorry, what it is, 921.6 kilohertz.
Okay.
Hey, 12 by 12, I'll get somewhere around divided by 32, you'll get 31,250. If you get this particular value, if you divide it by what value, you will get 9,600. Will you get 9,600 properly?
No.
If you divide it by any value, if you are getting 9,600 divided by some particular value, if you get the exact value 31,000 divided by somewhere around 3, you will get 10,400. Okay,
Okay.
if I divide it by 3, I'll not get 9,600, but I'll get 31,000 sorry, 10,416. If you divide it by 2, 31,250 divided by 2, you will get somewhere around 15,000. And if you divide it by 4, divided by that is the reason you go for 11.0592.
Okay.
Is it clear why we are going for 11.0592?
Yeah.
Only for serial communication we are going. Otherwise you can use any value depending on your data sheet, that you can go for any value which is in between 1 megahertz, or if you don't even use in place of crystal oscillator, if you use even switch, then also it will work properly. Just to make that switch 10 10 10, then also it will work, no problem. But generally we go for this 1 megahertz to 24 megahertz, any in between, any value you can use depending on the data sheet we will have to see. But for 8051 we are going for 11.0592, but that again, that is not same for AVR PIC or STM32 controller. Okay, that also again we will communication and you will have to write it. Okay. Is it clear?
Yeah.
Okay. Again you are using some SFRs here, which is SBUF register, SCON register, right? Then we have seen TCON register, and we are using timer here, so we will be using TL, TH, TCON. All these registers are there in SFR, that means from some address called ATH to FFH in SFR RAM. Okay, all these registers are predefined and they are therein. You will have some particular address for these bits in SFR RAM. Now we will write one program for transmitting and receiving your data. I hope it is clear. Why? Because it should be clear. The thing is, why it should be, you go for anything, any other controller also, the concept will be same. Now the concept doesn't change.
Okay.
For serial communication, for interrupts, timers, these concepts will not change.
Okay.
So in key, we will be able to see what we are sending, but we can't see what we are receiving. Okay, why we can't? And that is because receiving, we are doing it from external world, right?
Yeah.
And our software is not receiving anything from outside. So here we will see only for transmitting, and in Proteus we will see. Now, as I said, first thing what we need to do is, first we will have to select the speed, right? But when you want to use timer, first you need to select a timer, right? And we are using timer 1 mode 2, that we can select in register called TMOD register, right?
Yeah.
Right. So the value for TMOD will be 0x20, which is timer 1 mode 2.
Okay.
Okay. Then we will have to load one particular value in TH1. Okay. So I'm using something like 0xFD. Why? Because we are using 9600 baud rate. So FD, FE, FF 3.
Okay.
Okay. Next, now what we need to do is use your SCON register, and as I said you, we will enable your receiving option also, so the value becomes 0x50.
Okay.
Okay, we are using 01 for serial communication mode 1, and rest of all the bits are zeros. Receiving enable is 1, so that's why here you will have SM 0 as 0. This is 01 is for mode 1. Next bit is SM2, which is for multiprocessor communication, so it becomes 0. Fourth bit is receive enable, which we are making it as 1. Next is TB8, RB8, transmit interrupt, receive interrupt. So this becomes 0x50. Okay?
Okay.
Fine.
Yeah.
Start your timer. Once you start your timer, your baud rate starts, and then what we are doing is we are sending some particular bits of data, and now what we are sending is we need to load that particular value in a buffer register. So I am loading something like A here,
Okay.
and then we have to wait till my transmission is complete. Okay, so how I will
Okay.
know? Once you load and once you start transmission, SBUF after transmission, it will transmit 1 bit by 1 bit. So once it is done with transmission, your SBUF becomes empty. Once it becomes empty, you have one bit called TI, which is transmit interrupt flag will be back. So what we will do is we will wait here till Ti by default the value is 0. While my 0 is equal to 0, stay here only. Semicolon indicates here only as your while loop is true. As soon as it becomes 1, while my 1 is equal to 0, condition fails. It will come out.
Okay.
Okay, and then clear your flag. Ti equal to 0.
Okay.
Okay.
Yeah.
This is clear?
Yeah.
Just a second, I have some cables.
Yeah.
Avinash? Oh, Avinash. Avinash? Avinash? Yeah, the wire जलने की smell आ रही है. Wire जलने की smell आ रही है.
वो कोयला का है.
Hello?
Yeah.
So I'll just run this program now.
Okay.
I have error here. I didn't see. What is that error?
I'm seeing only the drawing board. Huh?
Oh, I have written O in place of 0. Fine. Now here how to see this is, now already my defined data, A is a defined data, right?
Okay.
I am not writing it any data in real time. Already some predefined data which is there, I am sending it, so I am able to see that in key. Now here what we'll do is, in this is receiver, and then you have one more tool called see, in view you have one uh, serial window. In view
Okay.
serial
Hello.
UART 1. Okay, I'll just use this. See, here it is.
Hello.
UART 1 right side. Now I'll run it. Okay, here step by step debugging will not work. Why? Because it will take time. Why? Because till it transmits, we are using something like our timer should be becoming one continuously, right? Because our timer should work continuously, it will take time. So that's why we will simply use run. If we run when you do step by step also, it will work properly, but it will take that much time because our flag should become one continuously. So till that time we will have to make it like click on it continuously. So here if you see in serial channel, mode is 8-bit mode, SCON register value, SBUF register value is loaded with 65 is nothing but 41 in hexadecimal. TB8 and RB8 are not loaded. Receive enable stick, this baud rate is 9600.
Hello.
Is it clear?
Hello.
If it is, then I'll just stop it and go with your Proteus. When you say Proteus here, I'll just share Proteus screen with you.
Hello.
From that time you are not able to see program. Oh, whatever I am executing you're not seeing, right?
Yeah.
Seeing only whiteboard. Oh shit.
Yeah, I'm
So sorry.
trying to tell you. I think your and I are not receiving my.
Actually I'm thinking that you are able to. I'm so sorry. So here if you see this, you're able to see this now.
Yeah, now
I
it's.
could not hear you actually, and in between your voice was like. I thought you are able to see. Okay, fine. I'm sorry. So here you see the
Okay.
tmod value loaded, th1 value, scon value, as we said, 101.
Yeah, that's
Start
fine.
your timer. Wait till
Okay.
load the value. Wait till interrupt becomes 1, and then ti equal to 0. Okay.
Okay.
Timer, th1 value, scon value. Start timer. Load the value. Wait for flag to become 1. Make flag equal to 0. I'll run it again for
Okay.
you.
Okay.
This is your serial. Here in view you have one window called serial window. Okay.
Okay.
In serial window you have UART1, UART2, UART3.
Okay.
So here we are selecting UART1.
Okay.
This is UART1. Right side down. You can see, I think, UART1.
Hmm. Yes.
Okay. Now when you run this, here you can say, this way whatever we are transmitting we will be able to see.
Okay.
Okay,
Yeah.
fine.
Yes.
Hello. Shall I stop debugging?
Hello.
Hello. Is it audible?
Hello.
Is it audible? Your voice got. Hello. Is it audible?
Yeah.
Hello. Okay. Here you can see something like here also we will have one terminal.
Okay.
Okay. You can see that terminal. You're able to see Proteus.
Yeah.
So here you have this option. You can see virtual instrument mode. Here you have generator mode, scope mode, and then you have virtual instrument mode. On my cursor is there on it. Virtual instrument mode. If you click on it, here you have something like logic analyzer and oscilloscope, and here you have one thing called virtual terminal.
Okay.
Okay, we need to select it. So when we click on this virtual terminal, here you connect this TXT to RxD.
Okay.
And RxD to TXD.
Okay.
Okay. We are doing no problem, but I am connecting it. That's it. Okay.
Okay.
Now we will load the program and see. See, you're able to see this virtual terminal, right? But I have loaded A and you're getting some different character, right? We should display, basically we should display A.
Okay.
But we are not receiving, we are not transmitting A. We are not able to, whatever your microcontroller is transmitting is A. But whatever we are receiving is not A. Correct?
Okay. Yeah.
Now here if you see, I have not changed the value. A, and we are writing A, but due to this frequency, now you see, it was 12 previously, and that's why we were not getting that particular data.
Okay.
Okay. This is for your transmission operation. Now we will write one program for receiving. So here if you want to receive something, see, you can write this program as a function also. Whatever you want to transmit, you can write it as function also. We will write one program later, but as of now, what we will do is, now we will change, or I'll just copy this program, otherwise again it will be late. At least I should complete interrupts today. I'll try to finish off 8051 today.
Okay.
I'll try. RX. Now we are writing one program for RX, and this we will not be able to execute in your 8051, I mean Keel software. Why? Because from external, how we are going to send it. So we will write our program, but execute it on Proteus only.
Okay.
So our T-mod value will be same, but as I am going to receive some character, I am taking one variable because I want to collect whatever we have received in. This is my unsigned cat, and now TH1 value I am keeping it same. If we want, we can change it to 4800 just to make it something like 4800 means you will have to load 12, which is nothing but FA. 6 you will have to, sorry, not 12. For 4800 you will have to load, in place of 3 you will have to load 6, which is -6 or FA, anything your wish. I am keeping it like FD. then SCON register is same, TR1 will be 1 only, but now here we will not load value in SBUF. We are going to receive value in SBUF. So here we are not going to use this TI value. Now first we will wait till we receive a data in SBUF register. Okay. As soon as we receive data in SBUF register, what happens is your receive interrupt flag becomes 1, right?
Yeah.
So okay, what I'll do is I'll just take this data in whatever variable we have taken, and that is my data. My data is equal to what we are using is SBUF register. We are collecting data from SBUF register and we are storing it in my data. Okay. Now what we are doing right now, okay, we will connect to LCD also, but for now what I'll do, I'll send it to port 1. Port 1 is equal to whatever data you have received, send it to port 1, display it on port 1, and then make this RI is equal to 0 such that it is ready to receive next byte of data. That means clear the flag such that it can receive next byte of data. This is my receiving program. Okay.
Okay.
The only difference will be for transmission, you need to load the value in SBUF first and then wait for it to transmit. While receiving, first wait for SBUF to become full and then you have to collect the data. Okay?
Okay. Okay.
Right. Is there any confusion or it is clear?
Yeah, it's fine.
In Proteus, I'll collect same thing. Okay, I'm running it now. No, I will have to load the program. Sorry. Mine is receiving. So I know that $41. Okay, so in port 1 I should get 41, which is 01000001, right?
Yeah.
So I will see my port 1 now. Oh, I'll send first. Now this virtual terminal will not display anything, but you will be able to type on it. Now I am typing A. Just right click on it, echo type the characters. If you have echo type the characters, then you will be able to see what you are transmitting. A. I am transmitting A, but it is not receiving it. Transmit is connected to RX3, yes, but then why it is not? I am not receiving it. 11.0592 megahertz crystal oscillator is connected. I'll just remove this RX3 wire also. But we are not receiving anything. That means some problem is there with our program, and that is, so here port 1, while my RI equal to 0, stay here. My data is SBUF port 1, my data RI equal to 0. So where exactly we are going wrong, we will see here. SCON, it is working. So we will try to do here. It is transmitting here, but you are not receiving anything here. You we have enabled the TH1 also, S1, FT0, XTR1. So everything is right only here. Displaying pause. Then why it is not displaying? There is no problem here, but still it is not executing.
Okay.
Can you see something which we are missing? While my RI is equal to 0, stay here only. My data is collected and send it to port 1. Make RI equal to 0. And that's it. Nothing is wrong with this program. Then zero. 11.059 megahertz, rated 9352. Then three. I'll just check it out why it is not working. It should execute properly, but I'll just check that out and I'll say you. Okay.
Okay.
Hello.
Yeah.
Okay. I'll just connect one. Okay. I'll just. Okay. We will try one more thing, but actually, without this one, or else the problem might be with the controller also. Why? Because we are using S52 and this is C52, but other than this I can't. Okay, here I can just check it out. 9600 parity non-stop bit. Send. Part value, baud rate is 9000 data bits, parity stop bits, exclude from this bits, text, it is 9600 only, why it is not receiving. Okay, I'll just execute this, but by the time I execute this, I'll just say next to topic. I'll be doing this, and along with that, I'll say you next to topic also. Okay.
Okay.
Hello.
Yeah.
Okay, because I don't want to waste time, so I'll just say you. Then I'll give you some program. So right, the programming includes only this particular registers. If you write that registers anywhere, then you will be able to work with this serial communication. Okay, so next comes your interrupt. Now, what are these interrupts? Okay, so basically interrupts are nothing but disturbances.
Okay.
Okay, when you get disturbed or distracted by something, first you will have to execute that, and then you can do your proper operation. Okay, so here also you have interrupts, but here interrupts are good interrupts, or you can say good disturbances. Why it is a good disturbance is because now you have some priority task given. Okay, when you have some priority task given, I can't be like if at all if I have some that it will be having some hazardous effects, like I get some sensor value. Okay, simply take your alarm value, alarm sensor. Okay, you get fire somewhere and your alarm detects it and send a signal to your microcontroller. But rather than saying that I'll work on alarm, first I'll say that I'll turn on LED, I'll ring the buzzer later. This will not work.
Okay.
Okay, so there we will have to use that sensor, that irrespective of what you are doing, first what you do is execute this particular operation and then do your regular task. Okay,
Okay.
so basically your interrupts are working like what you will say, generally we are doing step by step. When you are writing the program, all the things will execute in serial way.
Okay.
You have two things, one is polling method and the other is interrupt method. I'll show you both, what is polling and what is interrupt.
Okay.
So whatever you are executing till now is your polling method, and now that means whatever we are doing here, we are showing places. Whatever we are doing, what we are doing is simply one after the other work we are doing. First, if I use LCD, first use keypad, turn on LED, go for LCD, display the value on LCD, and then do all the things. Like that we are doing, one after the other. The sequence which we are giving, it is seeing that.
Okay.
Now if then also it is not receiving, or I'm not. Receive. there is no problem with program.
Okay.
Somewhere either the software is having problem or my it is getting stuck somewhere because it is not even stopping simulation. While connecting LCD, I will say you this otherwise. Okay, I'll just to check this out. I'll close the software and restart again. Till that time, I'll say intro. Okay, now suppose you have some task
Okay.
that you have something like 5 tasks to do in your program. Okay, and your microcontroller is working on it. Now when you say you want to turn on 2 LEDs, how you will turn on 2 LEDs? Hello, is it audible?
Yeah.
Okay, you will be turning it on one after the other, right? You will not be able to turn on 2 LEDs at a time. I
Okay.
want to turn on first 2 LEDs. So I will be writing something like S bit LED 1, S bit LED 2. Then you will be writing LED 1 equal to 1, LED 2 equal to 1, right? To turn
Yeah.
on LED. So you are not going to turn on both at a time. Or if you say, okay, you can say that I'll give whole port value, fine. But if you are displaying on LCD, then will you be able to display on LCD as well as your LED, turn on LED at a time? No. Either you will be able to display on LCD and then turn on LED, or first turn on LED and on LCD, right?
Yeah.
Whatever program we are writing till now, we
Yes.
are executing it serially, right? So
Yeah.
here you have your microcontroller. So what your microcontroller is doing is, first it is checking for first one and then it is executing 2. So if
Okay.
you have some sensors or something like that, it will check whether it needs its help or not. Now I'll be checking, okay, my first switch is on, then what to do? Okay, if it is on, what to do? Execute it.
Okay.
If you don't have, then what to do? Go to second task, then check for third task, then check for fourth task. Now if you see your keyboard only, you are checking, scanning continuously, you are scanning whether any key has been clicked or not.
Yeah.
Okay, so if it is clicked, then what it is doing? Okay, this has been clicked, execute it. So what it is executing, it will find out which key has been clicked and then display it on LCD.
Okay.
One GPS, one GSM, one sensor, one LCD, or one more device, something like Bluetooth. So you have all these devices connected to your microcontroller. So your microcontroller will be checking it continuously that whether anything needs controller's help or not. Because
Okay.
you, while writing program, you will be writing it that way. If not do, check this. If not this, check that. Okay, this particular thing of execution is called polling method. Okay, you
Okay.
can't, here what happens is, after 1 you will be checking 2, but after 2, if at all suppose fifth device needs your help, that means suppose you have received one character, like received one
Okay.
character in SBUF. Okay, but what I wrote is, I have written all these programs first. I will first check one LED 1 is 1 or not, LED 2 my Ri equal to 0. This particular statement till I receive, I'll not be able to check even though I received data in SBUF register.
Okay.
You you understood what I am saying? Here I'll be writing we are writing everything step by step. So even though you received some particular value in your SBUF register, till I go and check, I'll not be able to execute it. So after 1, I can't come to 5th task directly. I will have to go for 1, then check 2, then check 3, then check 4, and then only I can execute 5.
Okay.
Okay, I'll show you. Here I am writing something like, I am writing my one program. Okay, LED 1 equal to 1. LED 2 equal to 1. I am just writing this, just for example. And here I'll be writing while my switch is equal to 0. I am writing one switch function. So here I am writing my switch is equal to 0. Now what I am trying to say you is, when my switch becomes on, okay, this is my switch function. When I am executing LED 1, at that time if I go on turn on my switch, will it work? No. Okay, first it will execute this LED 1 equal to 1, then it will execute LED 2 equal to 2, then only it will come to this particular statement. Till this time, if at all if your switch is on also, it will not do anything and wait for its turn to come.
Okay.
Okay. Same thing what I am saying is, if at all if you are at first statement and if 5th statement needs some action, then also after executing 4th, then only it will come to 5th. Okay, fine. This is your polling method.
Okay.
So this becomes like, if at all if I needs help and still I am executing 1, it is not, in some cases it's not good. So we are going for interrupts. Now what your interrupts will do is, here is your microcontroller and it will be connecting your interrupts with this. This is my first device, second device, third device and fourth device. Whenever your device needs help, your microcontroller will be executing one set of statements continuously. Whenever your device needs help, that will come to microcontroller and say that I need your help, and your microcontroller, whatever it is executing, it will stop that work, first attend your first device which came to it, and then it will execute that, and then it will continue its operation. That means if microcontroller is executing some set of statements, first device, and then it will come at this particular position and starts its execution.
No.
Okay, this is work of your interrupt. Is it clear? Why you are using this?
Yeah.
Here you have something like masking.
Okay.
Okay, so masking is simply, you can say, ignoring. You have that masking option in interrupts, but you don't have that masking option in polling. I can't ignore any set of statements in polling, but I can ignore some of the devices. Now when I have 4 interrupts, only 1 came to me. That means 2, 3, 4 I can leave it. Okay.
Okay.
This particular thing you call it as masking. Even though you have 6 interrupts, you need not use all 6 interrupts. Only 1, 2, 3, whatever, how many number you want you can use, and rest of it you will simply hide it. That you call it as masking. Okay. So how does this execute? So first of all, your main program will be executing. Okay. As soon as your interrupt occurs,
okay,
what it will do is, you will have one function called interrupt service routine, ISR, interrupt service routine. One set of statement will be there. As soon as the main function is executing, what it will do, the next instruction address it will save, and it will switch the control from main function to your ISR, interrupt service routine. Okay, it will go there, execute it, and again it will come back to the address you saved. Hello?
Hello.
Is it clear or no? If it is not clear, you can say. I'll try one more way of saying.
You can tell that polling method.
Sorry?
Yeah. Can you repeat once?
Yeah, sure. I'll say you.
Okay.
One minute. Okay. Now, here you have some. This here, okay. I'll say you here. I have some ISR. ISR is interrupt service routine. Okay.
Okay.
Think it like some program.
Okay.
Okay. I'm writing one function. Fine. This
Yeah.
is my particular interrupt function. Now I'm
Okay.
using my main program. I'm executing my main program. I have some set of statements like okay, this is my set of statements I'm writing. I'm executing this particular main function. Now what happens is, at this particular position at G, I got an interrupt.
Okay.
I received an interrupt here.
Okay.
So what your microcontroller will do is, it will stop your execution here. It will save, TDH address is there, this particular line address, it will save.
Okay.
Next instruction address will be saved. That means now my program counter, generally what we do, program counters save instruction to be executed, next instruction to be executed, right? So program counter address of this TDH line. Okay, this is some set of statements. Okay, I'm writing some garbage values, but this is your address. Okay, now this address of TDH will be stored in PC. Okay, then it will shift this control from G to your interrupt service routine. Here I have some set of statements. It will be executing this first.
Okay.
And after this execution, after these three set of statements are executed, again it will go to program counter, get the address of this TDH and start executing it again. Okay, this is how your interrupt works. That means your main function is leaving it as soon as you receive your interrupt.
Okay.
Irrespective of what is the execution. Okay, it will not leave G in between. Okay, this set of statement itself completes the execution. Next line it will not execute. So present line it will execute and it will leave that.
Okay. Yeah.
Okay, so here we have in 8051 we have 6 interrupts.
Okay.
One of the interrupt is reset. Now, this interrupt, I think you can understand it very easily. Whenever you restart your program, whatever function you are doing in your laptop or in your phone, once you click on restart, it will stop the execution of everything and it will restart.
Yeah.
Right? Okay. I'll give you your phone example only. When you are getting a call, irrespective of what you are seeing, suppose you are seeing your YouTube channel or you are seeing some movie.
Yeah.
For a second, it will pause, or nowadays it is not pausing, but along with that it will show you an indication that you are getting a call,
Yeah.
right? That means you are calling, someone is calling you, that is okay. Someone is
Okay.
calling you, it is an interrupt. Whatever option you are, whatever thing you are operating on, first you will, if you want to receive the call, what you will do, if you are watching a movie,
Okay.
you can't watch the movie and talk on phone at a time.
Yeah.
What you will do, you will pause your movie, you will receive the call, you will finish that call, and then you will come back to your movie,
Yeah.
right? This is
Yeah.
same thing happening here.
Okay.
That's the high priority interrupt. Even though if you are not answering your call, even if you want to reject it, then also you will have to do that option.
Yes.
Or if you don't receive, you don't answer, don't decline it, then also that notification will be there on your screen, even though you are
Yes.
playing your movie.
Yeah.
So that call is your interrupt. In simple terms, is your main program.
Okay.
Fine. So here
Yeah.
you have reset option. Reset is also one of the interrupt. Whenever it occurs, everything is reset to 0. Then you have
Okay.
one thing called external interrupt. External interrupt 1. External interrupt 0 is first. 0. And then you have next you have timer interrupt is also there. Timer 0 interrupt. And then you have external interrupt 1.
Okay.
And then you have timer 1 interrupt. In timers you have for external you have two external interrupts, interrupt 0 and interrupt 1. In timers also, if you remember, we have seen one register called tcon register.
Yeah.
Not tcon register, as well as one more register we have seen in timers. There I said you that 4 bits will be using now and 4 bits will be using later, right?
Okay. Yeah.
So here we will use that register now. And then last one is your serial register, serial interrupt.
Okay.
Okay, now why you have only one serial interrupt? You don't have any interrupt for transmission. You have right? Why you don't have? Actually you can use, but generally what you will do, when you want to make a call, you don't need an interrupt, right? You will only
Yeah.
pause your, no need of saying, your phone will not say you that you need to make a call. You will
Okay.
only stop the operation, you will do call. So you don't need an external interrupt to say you that you have to make a call. But when you receive a call, you don't know from whom you are getting a call.
Yeah.
So generally for receiving we will be using an interrupt. For sending we don't use interrupt, but it's not necessary. Now what happens is, what I said is your interrupt service routine. Okay, or you call it as interrupt handler. What does this interrupt handler contain is, interrupt handler, once it executes, once it is you get an, okay, once you get a call, either you have 2-3 options, right? Answer, decline, or leave it, right?
Okay.
You will have to
Yeah.
do one of it. Here also, when you say you have one interrupt, what you will do, you have received the value. What you will do, just select it from list of register and clear the flag, right?
Yeah.
Right? The same thing will be there in this interrupt handler. Interrupt handler is a small 2 to 3 lines of code which is
Okay.
executed. set of statements, what will be there is clear the flag. That's it.
Okay.
Okay, so this is already there at particular location. ISR, you are not writing any interrupt handler. Already interrupt handler is there at particular ROM location.
Okay.
Okay, you'll
Yeah.
simply call it. That's it.
Okay.
You will have some ROM location which you have to see in your data sheet. You will have to see that in data sheet.
Okay.
Okay. Now, how to
Yeah.
enable and disable your interrupt? How to enable and disable your interrupt? You have now, for this also again you have one register called IE register. Okay.
Okay.
Which is interrupt enable register. IE register. Hello? Hello? Is it
Yeah.
audible?
Yeah.
So here also when you have an interrupt enable register, you have here EA bit. Next one bit is not there, it is reserved. Then you have ET2, ES, ET1. Then you have EX1 and ET0 and then EX0. So what
Okay.
interrupt you have here? EA, you have 6 interrupts. One is reset. If you reset is an external interrupt which you are using like switch. If you click on switch,
Okay.
your reset will work, right?
Okay.
So here we are
Yeah.
not using it. So here you need not enable it, but for other interrupts, other 5, we have these 5 bits, which is external interrupt timer. For timer,
Okay.
if you want to work with interrupts, first you will have to enable this particular bit, 8th bit,
Okay.
that is EA, which is interrupt all, enable all. If you make this
Okay.
bit 1, all the interrupts will be enabled. Enabled in the
Okay.
sense all the values will be 0. Whichever interrupts you want to work with, just make that particular bit as 1. I want
Okay.
to work with serial communication, just make this particular bit as 1. Then all other interrupts will be 0, but only one ES will be 1.
Okay.
Okay, so this is my interrupt IE value, IE register value. If you load this particular value, only ES will work.
Okay.
Fine.
Yeah.
0. Okay, so here you have to enable this particular bit. To enable or disable any particular interrupt, you will have to make that particular bit as 1 or 0. Okay,
Okay.
so this is your IE register. Now how to program this particular interrupt? Okay, now suppose you are using timer interrupt 0. Okay, so what
Okay.
happens is, if you are using this timer interrupt 0, first what happens whenever you get when you will get an interrupt in we were writing something like this now, while my TF0 is equal to 0, while my TF0 is equal to 0, stay here only. and when it becomes 1, go to next statement, right? You
Okay.
remember? You have one statement, okay? If you will see that again, you will recollect. So till this, that means what, till overflow occurs, it will be staying here only.
Okay.
Fine. So for this to work, so what happens whenever this TF, now you will not be writing this particular statement in your main program. This wait will be done by interrupt.
Okay.
Okay. So basically what happens is whenever your overflow flag happens, now your interrupt will inform main function that overflow occurred. I'll not be waiting for overflow to occur, my timer overflow to occur.
Okay.
Interrupt will wait, interrupt will see if overflow occurs, it will inform microcontroller that overflow occurs and clear the flag.
Okay.
Microcontroller, what it will do, clear the flag, that's it. So basically this wait time will not be there. Just now we have written serial communication program, right? Here I have written while my Ri equal to 0. So every time I will have to check that whether I have received data or not, right? This will be done by my interrupt. I'll not write in my main function, I'll not write this particular set of statements.
Okay.
This will be done by interrupt. But as soon as interrupt occurs, it will receive the data and then I will write this one. This statement, that this while statement I'll not write. I'll simply take the data from SBUF and clear the flag. That's it.
Okay.
Be there. Waiting will be done by interrupt. While writing program, I think you will understand. We will write 1 or 2 programs such that it will be like clear for you. Okay, now again serial interrupt and timer interrupt is okay. You have external interrupt. External interrupt can be something like sensors or switches, anything. Okay. And then you have here level triggered as well as one more you will have either level triggered or edge triggered interrupt. Okay, now I'm receiving something like what is this level triggered or edge triggered is, you will have some waves like thing, right? What you will call, not waves, you're able to see. Is it audible?
Hello.
Hello, is it audible?
Yeah, now it's audible.
Yeah. Okay, so here you have 2 types of external interrupts. One is edge triggered and the other is level triggered. Okay, level triggered is simply like either the level is 0, high, 1 or 0. This is your level triggered.
Okay.
Okay, when you say edge triggered is nothing but from high to low or high to low or low to high.
Okay.
If you are getting an interrupt at this particular thing like high to low, whenever I get from high to low statement, then then interrupt occurs, then you call it as edge triggered. When you have level triggered, interrupt will occur when your signal is either high or low.
Okay.
Okay. If go to 1, then you call it as edge triggered interrupt.
Okay.
Okay, so I said you that in we have 2 bits. We have used some TF1 and TF0 bits in one timer register, which was timer control register, TCON register. So at that time, I said you we will be using 4 bits now, and we will be using 4 bits later. 4 bits will be using when we are going with the timer.
Okay.
Okay. So now we have that one. Now that 4 bits we will see now. You are
Okay.
able to see notepad?
Yeah.
If notepad is visible,
Yes.
and then you have 4 bits. IE1, IT1, and IE0. If notepad is visible, hello?
Hello.
Yeah, if notepad is visible,
Yeah.
okay. So here in TCON register at that time we have used only TF1, TR1 and TF0, TR0. This is to start and stop the timer and to check the overflow of timer 1 and timer 0, right? And I said
Yeah.
that the rest of the 4 bits we will discuss in interrupts. Now these 4
Yes.
bits are for interrupts.
Okay.
IE1, IT1, IE0, IT0. Now IE1 is for external interrupt 1 and IE0 is for external interrupt 0.
Okay.
Edge triggered, that means from low to high or high to low transition occurs and external interrupt occurs. We are using this IE1. This becomes
Okay.
1. Okay, and it is cleared by CPU. When
Okay.
your interrupt is processed, that means whenever interrupt occurs, what should do? If at all, if I want to do some particular task like answer or decline, then the rest of the flag should be cleared by your CPU. Okay, this is for
Okay.
external interrupt 1, edge triggered interrupt. That means from high to low transition. Okay, next IT1 is for setting or clearing that particular edge. Either you want to go for edge triggered or level triggered.
Okay.
Timer external interrupt 0 and IT 0. This IT 0 or IT 1 is used to select whether you are using your edge triggered or level triggered interrupt. And if you are
Okay.
using edge triggered, then IE1 is used to say that whether it has received a high to low signal or not.
Okay.
Okay, so this is about your T register, and if it is clear, then we will go with some programs here. Okay.
Okay.
Mm, okay. So we will write our program in your what it is. We will write program in Keel and then we will. At all, if we don't use this, then whether it is working. And it can, and it- okay, ठीक है. We'll see this also.